Yeah, we actually did a rough calculation with the Excel formula that we have currently, and we're basically going off of intuition in terms of the problem that you gave us for homework, I believe, a couple nights ago. It was finding the impulse of the stopper block on
Okay.
the catapult arm. Now, I believe that was from 180 to 125, I want to say, or 110, around there. And you gave us an omega to assume of about 30 radians per second.
Okay.
We just did our calculation of the omega achieved from 180 pullback to a 110 stopping angle, and we're calculating an omega of around 9 radians per second. And that magnitude is a lot less than what we should be expecting an omega probably of around 25 to 30.
Yeah, generally most people get more along that, which you just said, that's the 25 to 30. So can you show me, let's see,
Screen share, we can do that. Let's see if we can start that. Is that what you're asking?
But yeah, but what I want to see really is your rubber band curve.
Okay. Yeah, I can pull it up for you. It won't let me share it while you're sharing.
Okay, hold on. I can probably do something here. Let me pause my share, and let me see if there's other stuff I need to do. Can you do it now or not?
Let me check. No, it says still the same error message.
Okay, so I just stopped my share. Let's try one more. Can you do anything?
Yeah, there we go.
Okay.
Oh, whoa. Okay. Do you, can you see this?
I can now, yeah.
Okay, perfect.
So so the dimensions we have there are pound inches. We did make sure to correct for dimensions with our work energy. We will go back and see if that's an issue, but again, we did take that into account.
Okay, so I mean, is this for one or for two rubber bands?
This is for two rubber bands.
Okay, so I mean, if I just look at this, then I don't know if I can do any spot. Let me see if I can. You guys can't see my mouse, right?
No,
Not currently.
Let me see if there's anything I can do here. Hold on for a second. Oh wait, maybe I can annotate now. Let's see. Now, can you see my mouse?
No. I think that if you draw things, that it shows up though.
Yeah. Okay. So basically, what I would do is at 180, what was your length of the rubber band?
For 180, we got a rubber band length of about 28 inches.
Okay. So like this would be like right here. Yeah. Can you see that?
Yeah.
Okay. So that would be here, right? And then what was it? Yeah. So don't move your screen around now.
Sorry.
So go.
Okay.
So, okay, so let me see. So basically, can you make it bigger like it was before? Because that'll be easier.
Yeah. Does this work?
Yep, that's good right there. Okay, so then basically what I'm saying is, like right there is where your 28 was, and then what is it at, say, either 125 or 110?
At 110, we got a rubber band length of about 19.
Okay, so basically then, there you're looking at about a foot. Does that make sense? Like the difference going from here to there?
Yeah.
Right, so that's not too much different than a foot. Okay, so then right here, I'm trying to figure out what your energy was that you calculated, because really it should be this whole thing there, right? So if I was going to do a WAG, I'd say it should be like 11 and then 6. So I'm just doing a quick trapezoid type of roll.
Actually here we can look up
we have so what I did to calculate the energy was I took that equation that was provided by Excel up at the top, and I ran an integral on that.
Sure. And what did you? So I'm asking what you got.
So what we got for the stored band energy from a pullback angle of 180 to a stopper angle of 110 is 78.03 inch-pounds.
And that's about 6.5 pound-feet.
Okay, so I mean, that seems like it might be a little low if I'm just looking at it because, I'm seeing like right here it's 11, right? And then right here it's 6. So that would be like 17 times a half. So I would think it might be a little bit higher. But, I mean, even then, I'm surprised that would give you that small of a one. Like, what did you get? How much is your VG?
Let's see. VG calculated, I can calculate there right now. You just want the individual MGH value?
Yeah, or whatever your difference was, like how much energy is going into moving the
yeah. Oh, I mean,
sorry, actually, that stored band. Oh, no, never mind. I was okay. I don't know what I'm saying.
So Dr. Self, just to be clear, you wanted the change in potential energy for the work energy equation, correct?
Yeah.
Okay. Yeah. Let me get that for you right now.
Oh, due to the change in height.
Yeah.
Okay.
And then also, what did you do for your kinetic energy?
You mean in terms of how we modeled the equation for Excel?
Yeah, or what did you do even, sort of hand calcish wise?
Yeah, actually, I only have it on paper. Can I actually dictate to you the overall equation we were going to use to solve for omega?
Sure.
Okay, so the general.
But it's easier to actually break it down. It's always easier to try to debug by looking at, how are you setting up your kinetic energy? How are you setting up your potential energy? How are you setting up your elastic energy?
Sure thing. So, okay, are you ready?
Uh-huh.
Okay, so, and I don't know if this matters, but this is to solve for 110 degrees stopping angle. So omega is the square root, and then in the numerator, we have VE1 minus VE2, and that's again just the change in our stored potential energy from the rubber band, minus 0.0161 pounds mass times 32.2 feet per second squared times h of g.
Yes.
And
I don't have a good way to debug that. So the question is, does your VG have that much of an effect? And then basically I need to know what you did for your T2.
Okay. Well, actually, we just spawned another question. We were concerned about dimensions, basically like for example, the 32.2 feet per second squared being in feet, whereas most of our calculations are in inches.
Right.
I tried doing some dimensional analysis, and for me, it worked out that even though we were going to have all of our dimensions in inches, having a pounds mass times feet per second squared, it basically took care of itself. Because obviously, if you have a weight divided by g times g, you're just going to have the weight back again.
Yeah, but you're going to have mass in other places where you have to do it. So I don't know that you're going to, because mass doesn't cancel out of everything because you have your K. So that's why I said way at the beginning, I said change everything right away to feet.
Okay.
And pound force. So that could easily be what your issue is.
Okay. Yeah, like for example, our IO, because in the denominator of our omega equation, we have our IO value, and we changed our IO value to pounds times inches squared. Now, correct me if I'm wrong, but that pounds times inches squared is a pounds force times inches squared, right?
No, it's a pounds mass.
Pounds mass, even though
it's not even pound mass, it's slug.
Slug. Okay. So what if we took our IO and we divided by 32.2 feet per second squared? Would that help anything?
Well, you need to just be, so I wouldn't say just change stuff willy-nilly. You need to go back and make sure that everything, to start out with is in feet. and that, including your energy that you're going to do, so everything needs to be in feet and foot pounds. So because of G, that's why I always say we should have gone to the metric system, but you need to get practice with this stuff, showing you how you have to be super careful with it.
Yeah. Now our concern is that 90% of our work as it sits is in inches. That's what I'm concerned about, is if we go into, start trying to change everything into pounds again, including our force curve, that's going to be kind of a, tough situation for us. Would there be any way to basically keep going with inches?
Well, I mean, for most of the places, you're just dividing by 12, right? Wherever you had the inches. So
we are, yeah.
I mean, you could try, but the problem is, it sounds like you may have done it in some places and not in others.
Yeah. So with our force curve, the kinetic energy of the rubber band, we have our y-axis being force and length being inches. Now, just to be clear, you said that force, that y-axis of our energy curve for the rubber band, you said that was in slugs and not pounds force? Because
no. It's always pounds force.
Okay.
It's always slugs. So we don't use pounds mass ever in dynamics or statics.
So the force transducer was in fact reading pounds force.
If you, you had to put whatever, there's a little button you kept pushing, so I don't know what you had your button on.
It literally just said pounds. That's all it said was pounds.
Yeah, I mean, there's no way that that thing's a fisherman's thing, right? So there's no way some fisherman in Texas is going to have any idea what pounds mass is, right? So
likely it is pounds force.
Yeah, they don't go around saying, I just caught myself a 10-pound mass bass.
Yeah, exactly. Yeah, no point in doing that. Okay. Okay, so besides your recommendation of basically just backtracking and trying to figure out if our consistency with inches versus inches versus feet is correct, what other sources of error do you think we should be looking for in addition to dimensional analysis?
Well, like I said, how did you decide to do how did you end up doing your kinetic energy?
Kinetic energy, so the half IO omega
squared.
Yeah.
And what do you use for IO?
We're using 0.0122.
Slug inches squared.
No, slug
feet squared?
Yep, that's feet squared.
Yeah, and then we converted, and then our conversion to slug inches squared was 1.7568.
How? That doesn't make any sense. Oh, you mean the overall?
Correct. Yeah.
Slug inches squared. Okay. Yeah. I don't know. I thought you were saying that was a conversion factor you used.
Oh no.
Yeah. So I think you're going to get messed up because you've got some inches squared and you've got G in there, where that's just a single foot. And you totally have some sort of unit issue.
Okay.
I mean, it shouldn't be too hard
Just the
to.
dimensional analysis, basically.
I can copy this sheet.
Well, the thing is, I tried changing that to feet over inches squared, and what that does is that creates that creates a negative square root, which it's going to give us an imaginary number we can't work out of it. So it's going to be somewhere else. That's what I was able to rule out.
Have we accounted for the fact that acceleration due to gravity is also negative? So they shouldn't be subtracted; they should be added.
That's the thing. I mean, maybe I can try doing that really quickly.
I think that might, because
so you're gonna do. So we want to do inches per second squared.
Yeah. I'm gonna change this to inches, and then. Oh man.
Yeah, we're trying to do like back of the envelope calculations right now. Trying to figure out what's going on. So what did you say it was, Callum? 386.4. That's what I thought, and I'm hoping you're right, because it's going to be a mess of dimensions.
That
in that equation.
Man.
In that equation, that was the only one that was.
That was questionable. Because feet, all the others are inches. 6. Yeah.
I mean, it's gone up slightly, but damn.
Only slightly.
Yeah.
How?
I don't
Changing a
know.
number from 32 to 386, and all that change was.
I mean, it's under a square root. There's a whole bunch. There's so many things done to that number that you can't really.
So do this for me. Okay, so, and how much did you say you had for the integral under this curve here?
Roughly 6.5 pounds-feet.
Okay, so let's do, all I'm going to do to start out with is basically we're just going to say, well, what happens if all the spring energy went into kinetic energy, right? So basically you would have VE, right? Or the U due to like basically be VE2 minus VE1. But basically all that area, which you just told me was like 6.5, right? So let's just do a back of the envelope, would be equal to 1/2 I naught omega squared. Do you understand what I just said or not?
1/2. Yeah, no, I got you. I'm following.
So if all of the spring potential energy was converted into the kinetic energy of the arm, right?
Mm-hmm.
So now we would have 6.5 equals 1/2 I O omega squared. Is that good?
1/2 I omega squared. I O omega squared. So are you saying we should neglect the change in potential gravitation?
No, I'm just saying let's do a back of the envelope
Sure.
calculation.
Yeah,
Idea, right?
I got a 32.
You got a 32.
Yeah.
32 omega?
32.6 omega.
Okay. So maybe we should just convert to pound-feet then for
Yeah,
our
I agree.
potential. So we should just do a multiplier, or excuse me, a divider of 12.
Yeah,
there.
it shouldn't be too hard to go through and change.
No.
No,
Let's
not
do
at
that.
all.
Okay.
Yep. So now do this. So take the, now I'm going to solve for the omega squared and what I just said. So now do 2 times 6.5. You can do this in your Excel sheet right there, right?
Yeah.
2 times 6.5 divided by 0.01. What did you get for your IO?
0.0122.
Yeah.
Slug, what is that, feet squared? Slug feet squared. Yeah, slug
Okay.
feet squared.
So 6.5, that was in foot pounds, right?
Correct.
Okay. So do 2 times 6.5 divided by 0.0122.
Okay. 6. Do that. So that's 13 divided by
6.5.
That would give us a.
32.64.
Whoa. That doesn't. Hold on. 2 times 6.5.
Divided by
0.0122. That gives us roughly 1,065.
You have to square root.
Okay. Now take the square root. Yep, just like Wyatt said.
32 omega. Yeah, 32 radians per second.
Okay. So
That's definitely.
Okay.
It's definitely probably just a.
Cool. So let's see. So let's checklist here.
let me ask one more question.
Sure.
So let's go ahead and start thinking about how much because we just neglected the potential energy due to gravity, but let's get a little bit of an idea of what that'll be, right? So how much did the whole thing weigh?
Ball and arm was a combined weight of 0.0161 pound mass. So that times 32.2.
You mean slug?
Excuse me.
It's not pound mass.
Not pound mass, it's slug. Sorry. That is 0.0161 times 32.2 is about half a pound.
Okay, so if we got about a half a pound, and then, what's the maximum that thing would actually move from being totally straight up to totally down? That
would be a so if you were to go back to 180 pull back to a 110 stopping angle, that would be 9.1 inches. 9.1 divided by 12, you get about 0.75 feet. That would be your total, your maximum, basically.
Yep. So if I multiply about a pound, half a pound times 0.75, then I'm going to get about 0.37 in terms of my my total VG change. Does that make sense to you?
Yeah.
So that's going to be the only, basically that would be subtracted from the 6.5. So I'd do like 6.5 minus 0.4, And that's going to give me a pretty good idea of what my overall omega should be, right? Just by looking at kind of the amounts of approximation.
Yeah, because what you just said, that 6.5 minus 0.4 is your kinetic from spring minus your potential gravity.
Uh-huh.
Okay. Yeah, so that gives us. Okay. Okay. Yeah, that does check out actually. So, can you still happen to see our Excel sheets?
Yeah.
Okay. So what we think we should do is obviously convert our like how Wyatt is doing right now.
Oh, he can't see this one.
Oh, we can't see it. Okay.
Here, let me see if I can.
Yeah, can you do like a full screen
Yeah,
share?
I'm sure I can. There it is. New share.
Yeah.
Yes.
Is that popping up?
I'm going to say one more thing too. What was your unstretched length of your rubber band?
The unstretched length was
14.25.
14.25.
So that should your curve should also go through that. I don't know for sure if it does, but you should have a point at 14.250.
Let's add that in the data. Let's just add it.
Okay, just the 0 and stuff?
Yeah, just literally add it right now.
Let me, can I?
Yeah, right click. Shift down. There we go.
14.1?
14.25.
So who else is there? I got Wyatt and Alec, and who else? In the background.
Catherine
and Kellen. Catherine and Kellen.
Hi, Kat. Hey, Kellen.
Can you hear us okay through the background?
Yeah.
Okay.
What did we have on this? Smooth line? No, we had a trend line.
So I'd say also make sure you always keep your old, I usually, if I got something that I think is pretty close, I always save 2 versions, you know what I mean?
Yeah.
To make sure you got your old one because it seemed to be working okay.
No, I'm actually going to copy that onto another sheet before I continue to edit it, I think.
So it's our logarithmic.
Yeah, hold on a sec. Sorry, I'm just like, this is weird to.
And you understand why I say that should be 0 at that point?
Yeah.
Yeah, an unstretched should warrant to 0 pounds. God, we should have taken more data points in that head zone. Shoot.
Polynomial?
Yeah, polynomial to second degree. Or no, excuse me.
I'm not quite sure which one of these would be better.
So you're going to get similar things for the, so you probably don't want to waste time with me watching part, right?
Yeah.
So let's see if there's other main questions you have for me.
Okay, so we're going to convert our kinetic spring to pounds feet instead of pounds inches. That should solve the dimensional problem. So basically what we have so far in our Excel sheet is we have it up until actually once we figure out this little issue, our Excel sheet will be able to solve for omega. What we're hoping what will work out smoothly is we convert omega to velocity using v equals omega cross r. That will give us a vy and a vx. We use vy to solve for a time in which the ball will travel vertically upwards and then travel downwards. That'll give us a total time of flight, and then that total time of flight times our vx should give us a distance.
Yeah, and then you can check that with, like I said, there's some online projectile motion calculators you can always check with.
Okay. Yeah, it just seems like the dimensional problem was our main issue in that case.
Yeah. Okay. I think I think if we go through and change all the dimensions and stuff,
We should be fine.
we got a good,
Yeah.
you know, it's not like we don't know how to do it now. I think that, I think this looks pretty promising.
Okay. Well, make sure that, you know, like I say, because you're only going to have a minute or two. If I say 110 and, you know, 22 feet, then you got to be able to calculate that pretty fast.
Yeah.
Okay. Or you just have a table of what it would be.
Yeah, that
Yeah,
was
I think that's
plan.
our plan. But awesome. We'll get to work on that, and we'll email you if we have any like super important questions.
Okay.
Awesome. Thank you so much.
All right. See
Thank
you
you,
guys.
Doctor.
Bye. You too.
So just somewhere along